Okay, a little bit of bonus material here on limits. So there are some hard examples. Limits can be incredibly challenging. They can be nearly impossible, and you'd be surprised how often um, hard questions in math come down to: can you find a limit? A limit? Can you approximate it quickly? Can you get it exactly? And so I wanted to give two examples of how they can be counterintuitive, and one example that's actually coming up that we'll learn how to do or get more practice with in the future. But we'll kind of go through each of these three examples. So I like all of these. The first one is pretty special. The limit as x goes to 0 of sine of 1 over x. So to think about why this is weird, it helps again if we can sketch this real quick. So give myself a couple of places to draw here. Whoop. Okay, and so if I was going to graph just the sine of x part, I hope you know the sine of x looks kind of like this. Oops. Starts at 0, and then it has a beautiful sine curve, and it goes back. It's an odd function, so it rotates direction kind of like this. Okay, now this is sine of x. It goes up and down. However, the thing inside of it is 1 over x. And that is going to get very, very big, very, very fast. So rather than just seeing 0, it's going to see increasingly big functions. In fact, just to remind you, sine of x looks kind of like this, not to scale. Okay, sorry, 1 over x looks kind of like that. So as we get close to 0, that thing inside is actually going to infinity. So that thing inside is going to go faster and faster and faster and faster and faster, which means it's going to go through more and more of these cycles quicker and quicker and quicker. So what would that actually look like? Well, I highly suggest you try to put this on your calculator or on a computer and zoom in a lot, but I do think it's best to try to do this by hand once. Say, okay, as I'm really far off, I'm doing this fun sine wave thing, and 1 over x is changing very slowly, so I have this nice long curve. But as I get closer and closer to 0, that sine of x is going faster and faster. It's going to go off to, in this case, negative infinity, which means I need to go through infinitely many periods of sine of x, right? Every 2 pi that this changes, I'm going to go through a single period, but this is changing faster and faster, and it's going to change infinitely much. And so as it goes faster and faster, I'm going to start cycling faster and faster. And I need to go up and down infinitely many times before I get to 0. Similarly, on the way back, it starts off nice and slow, and then it's going to change faster and faster as I go to 0. And because that inside of sine of x is changing infinitely many times, that means sine of x has to go up and down infinitely many times, going close to here. This is called the topologist sine curve. It's called a pathological example. I'll have a couple of really nasty examples for you throughout the course. And this is, so a pathological example is an example that is meant to break something. And this is meant to break your mind. This is not defined at 0. The limit doesn't care that it's not defined at 0, but I can't plug anything in here. Okay. Now the question is, what should this be converging to? What is this limit? And as I get close to 0, it looks like this function, well, it gets close to 1 as much as you want, and it gets close to negative 1 as much as you want, and it gets close to everything in between as much as you want. But I can't force it to stay close to any of those. It's also going to be far away from every single one of those values as much as you want, right? I could say, oh, it kind of looks like it's going to 0, but I say it can't be converging to 0 because it spends so much time close to 1, right? And it spends so much time close to negative 1. So to actually have a limit, I need to be able to force it to stay close as my x gets close to 0. And for this reason, we're going to say this limit does not exist. Okay, if that's a bit confusing, good. It's meant to be confusing. Think about it. It's fun. All right. So how can I maybe make something like this that does converge, that does have a limit? And so I might try to do something like sine of 1 over x times x. And if I think about this x as like an amplitude, So if I think of it like an amplitude, what it's doing is it is changing the height of this sine of x function. It's changing how much it alters by. So here's me trying to draw not sine of x, not x, but actually x and negative x, because sine is going to be positive and negative. So sine stays in between 1 and -1, and then it's going to be multiplied by x, which means that it needs to stay inside of this, the left and the right of this x here. So here I go again. It's being multiplied by x. So that's its height, and that amplitude is going to go down to this one. It's going to go up to here, and it still has to go up and down infinitely many times. It's going to go, and same on the other side. And then by the time I get here, something like that. I should probably add a few more wiggles in here. There we go. All right, there's my incredible drawing of x times sine of 1 over x. That's really all I need is a sketch to get a lot of insight. Do graph it on your calculator, on a computer, but actually I think this is the quicker, cleaner way to do it, is to not get caught up in all the zooming and rescaling that your calculator is going to want to do. So in this case, it still is behaving really weird-like, but you can see from the left and the right, it is being forced to say, the y value is being forced to stay very, very close to 0 as x goes to 0. And so in this case, actually, this crazy limit is going to be 0. Even though this curve here is sort of infinitely long, it's going up and down infinitely many times, really hard to even talk about plugging in anything close to it. But because that x is forcing those amplitudes closer and closer to 0, the whole limit's going to exist and be 0. Okay, those are fun. I like those a lot. There's lots of variations on those. I wanted to point out, hey, we don't have to get quite so out there to show that maybe we're going to need a few algebraic tricks. This is a limit with a square root in it. And if I try to plug in a 0, oh no, common mistake for me, mixing up x's and t's. Great. As t goes to 0, this whole numerator, 0 squared, plus 9, is going to be 3 minus 3 is 0. And this denominator is going to be 0. And I'm in this wonderful and terrible 0 over 0 place. And whenever you see a 0 over 0, what that means is not I can just cancel those zeros. It means I've got some work to do. And in this case, I also have square roots, which might be scary as well. And so I'm going to go ahead and just tell you what we're going to do in this case so you can get a look at the techniques we're going to use. And the trick here is something called multiplying by the conjugate. And the conjugate in this case just means, you see that sign there? Make it a plus. If this was a plus, make it a minus. I don't even care what order the radical is, but whatever sign you see, just flip one of them, and that'll give you the conjugate. And we want to multiply on top and bottom by the same thing. If I multiply on top and bottom by the same thing, I'm really multiplying by 1 in a fancy way, as long as t is not 0. And I'm allowed to do that. Algebra says I'm allowed to do that. This limit is telling me that I can ignore that place where t is 0. Actually, it doesn't even matter that t is 0 in this case. Luckily, you all know now how to multiply these fractions across. When I multiply by this conjugate, I need to FOIL it out. I'll do that real quick here. On top, I get this times this. When I multiply a square root by itself, I get a t squared plus 9. I'm only going to do this long ways once here. I get a plus 3, this times that, times square root of t squared plus 9 minus 3 times that is 3 square root of t squared plus 9 minus 3 times plus 3 is minus 9 over bottom times bottom when I multiply fractions, parentheses are your friend, t squared plus 9 plus 3. Okay, now the reason we multiply by a conjugate in this place is because if you do it right, these should cross out. So if you multiply by the conjugate, in the end, you should not have any square roots. This is the same thing with complex numbers. We multiply conjugates to get rid of the imaginary parts. So that's why we multiply by a conjugate. That's why after this point, I'm going to go a lot faster, and I'm going to skip those middle terms because I know they're going to cross out. In this particular case, it works out really nicely as well, that we also get this. The 9 and the 9 cancel out. That won't always happen just because they're conjugates, but in this case they do. And now we're just left with t squared over this t squared. I'm going to go a little bit slower here now and say this is t squared over t squared times the square root of t squared plus 9 plus 3. I'm going to also back up and include this limit. You should always include those limits until you've actually taken something out of it. Leads to a lot of confusion on both ends if you don't. And always use those parentheses. Okay, and I rewrote this because I want to show you that yes, we can cancel these out, but I also want to be careful here and say, hey, this t squared is multiplying everything on top, right? Secretly, you can imagine that this is like a times 1. Okay. I really couldn't cancel out this t squared here. This is just a reminder of your algebra skills, right? I can't cancel out this t squared right off the bat until this other stuff is gone. You need to factor it out first. We only get to cancel out factors. We can't cancel out things with plus signs in them from the top and the bottom. Sometimes people get going fast and they make that mistake. Okay, so what is left? 1 over this whole thing. If I plug a 0 into this, it looks like I would get the square root of 9 is 3 plus 3 is a 6. That's beautiful. I can just plug in now and I'm going to get a 1 over 6. Amazing. All right, I will make sure to include lots more challenging limit functions in the future. I'll try to even throw in some really bizarre ones because I think they're fun. And just a reminder that limits are challenging at first, not just because of the algebra, but because of the language. Practice talking about them, saying them out loud. Make sure that you understand some of those definitions and the different ways of looking at them using algebra or graphs. In the end, it's really easy to forget that really what limits are to us is an amazingly precise language that is where they're going to have their value often for you after calculus. Even after we've used them for what we need them for in this class, limits are amazing for talking precisely about infinitesimals and infinites and behaviors of things that otherwise can be very problematic for hundreds of generations of many, many mathematicians. So be grateful that this foundation is laid down for you. All right, until next we talk.